Next, we're going to talk about potential. That's a really super useful idea and probably something you're already a bit familiar with. We're going to build up the idea of potential by comparing it with gravity, just like we did with the electric potential energy. So, super fast recap here. UG, which is mgh, is our gravitational potential energy. It's the energy that mass m will have when it's at height h in an area with field g. What is g? So we said that g was our gravitational field, and it was the gravitational force divided by the mass. Another way to say that is force per unit mass. If you want to think about what that is, it means if we put mass m in an area with field G, it's going to feel force F. Okay, we did that when we talked about electric fields. So what if instead of doing force over mass, we did energy over mass? So gravitational potential energy is mgh. Let's do the energy over the mass. UG over m is equal to g, gravitational field, times h, the position. That's the energy per unit mass. So what does that mean? It tells us if we put a mass at height h in a field g, it's going to have energy U. And the energy per unit mass is something called G times H. This is actually something called gravitational potential. I don't guess you're very likely to come across it. Astronomers use it more than anybody else. So if you're interested in following the astronomy field, you may as well get used to it. Otherwise, we don't talk about that loads, but it's still totally a thing. Energy per unit mass, just like force per unit mass is a thing. Let's develop the same set of ideas, but let's talk about it with electric fields. What is the energy per unit charge, right? We're not going to ask energy per mass because that's gravitational. Energy per mass is going to be something important. So our electric potential energy, UE, is equal to charge times electric field times the position. Remember we said S equals 0 at our negative plate, and S got bigger as we go away from the negative plate. So U is equal to Q times E times S. So that would be our Q outside of E times S. So our electric potential energy divided by our charge is equal to something called E times S, the electric field times the distance. This gives us the energy per unit charge. That can be a very useful concept, and we call this concept the energy per unit charge. We give that a new symbol. It's got a symbol of V, and we call it the electric potential. That's a new thing, and we're going to spend just a little bit more time talking about it on the next slide before we start getting into examples. So let's get into electric potential a little bit more. First, we're just going to really hammer home that idea of the comparison between the force and the field and kind of that idea and how this goes together. So when we put a positive charge Q in an electric field E, it feels an electric force Fe. And that force would be to the right in this picture. There's our electric force Fe. That electric force is equal to the charge plus Q times the electric field E. And the electric field can be thought of as the force divided by the charge, or the force per unit charge. Things to pay attention to here is that our little charge Q, when we put it in the electric field, it gets the force. Force and field are both vectors, and E, the electric field, is the electric force per unit charge. Okay, let's keep all of that in our minds, and let's talk about electric potential and electric potential energy. If we take a positive charge and we put it in some area that has a potential V, then that charge is going to have an electric potential energy. Okay, so if we take a charge Q, I think I'll just call that Q, I won't put the zero on it. If we take a charge Q and we put it in an area with some electric potential, remember that had a symbol of V, then that charge Q is going to have electric potential energy that we call UE. And that's equal to the charge times the electric potential. Okay, so this stuff is really similar to fields and forces. Let's see, what will we say next? If we move the charge around, if we move it to a new position, it's going to have a new electric potential energy. So that means we can get a change in electric potential energy if we take a charge and we move it around to areas with different electric potential. So if we change the potential, we change the potential energy. That makes sense since potential energy depends on potential. We can solve our expressions so that it gives us an expression for potential. So our electric potential is the electric potential energy over the charge. That's familiar from our last slide. Or our change in electric potential is our change in electric potential energy divided by the charge. So energy per unit charge again. Okay, a little bit of housekeeping to do. The units of electric potential are volts. Volts has a symbol of V. This is confusing. I know it's confusing, but this is the way it has always been since people started talking about this. So way back when, first we started talking about potentials, they decided to call that V, and they gave it units of volts, which is also symbolized with a capital V. If you would like to change it, then I do invite you to write a new physics book and try and sell it. I promise you I will buy a copy because I don't like it either. In printed text, the symbol for potential V would normally be given in italics and the units would not be italicized, but you can pretty much always get it from context. There is another thing about electric potential. It has a whole whack of different names. So when I say electric potential, you could also call it electric potential difference. You could also call it potential. You could also call it potential difference, and you could also call it voltage. So it has a whole stack of different names. Depending on what book you're using and what person you're talking to, you might hear any of those things to identify potential. I'm going to try really hard and always use the phrase electric potential, but chances are good that I'm going to slip and call it potential sometimes too. But that's pretty much what I'll stick with. And what's the last thing we'll point out? Oh yes, electric field, like we have drawn on the left, that's created by those two plates that we have in the picture. So an electric field is caused by some sort of outside charge. It's called a source charge. Electric potential is the same thing. Electric potential is caused by those same source charges. And when we put a charged particle in an electric field, it feels a force. When we put a charged particle in a potential, it feels an electric potential energy. Okay, next we're going to keep going with some of these ideas. So far we've discussed force and field, potential and potential energy. Now it's time to start talking about electric field and electric potential. How are E and V related? How do they come together? So we already know charges move towards lower potential energy. We're also going to ask, how do they deal with potential? So lots to talk about here. We know that outside charges, source charges, cause electric field. They create electric field and electric potential. We'd like to know what that relationship is. So let's start with our picture of a positive charge in an electric field. We'll remind ourselves what happens to it. We know that it's going to feel a force that points to the right because force is charge times field. If it feels a force that points to the right, it's going to move to the right. Eventually, it's going to get over here to the negative plate. So our initial position is over here at the positive plate. Our final position is over here at the negative plate. Let's look at what happens to the electric potential energy. our initial electric potential energy is equal to the charge times the electric field times the position. And our final electric potential energy is equal to the charge times the electric field times the position. But remember, the position at the negative plate is 0 because we picked our negative plate to be like ground. Okay, that's our potential energy. We've done that a couple of times now, so it's not so confusing anymore. Let's layer in our electric potential. Electric potential initial is going to be the initial electric potential energy divided by the charge Q, and it's going to be E times S. So QES divided by Q gives us ES. Our final electric potential is our final electric potential energy divided by our charge. So 0 over Q gives us 0. So what we see here, if we take a positive charge and we release it from rest, it's going to move towards lower potential energy and lower potential. Now we remember with charges that they always throw a wrench in the works because they can be negative. So let's ask about what's happening there. Let's just make one extra note first. We notice that our positive charge moved from the positive plate towards the negative plate and moved from an area with high electric potential energy to low electric potential energy, or high potential to low potential. So let's label our positive plate as having high potential, or an area with higher potential. And our negative plate is an area with low potential. Okay, that clues up talking about our positive charge. Charges are different from masses because we can have a negative charge. Let's see what a negative charge does. Now for our negative charge, let's take a little negative charge and let's release it near the negative plate. So let's put our negative charge here. We know that our negative charge is going to feel an electric force. The electric force is going to be opposite the field because our charge is negative, which means it's going to move to the left. So if our initial point is at the negative plate, our final point will be over at the positive plate. Let's think about our electric potential energies. So our initial electric potential energy, whoops, I made an E where I meant to make a U. Our electric potential energy initial is my charge minus Q times the field times the position, which is 0. My final electric potential energy is my charge minus Q times E times my position. Now I'll find my potentials. V initial is the energy over the charge, so 0 over Q is 0. And my final potential is my final energy over my charge is E times S. Okay, so no surprises here. We see that our negative charge, when we release it from rest, also moves towards lower potential energy. It goes from 0 to some negative value. But what it does with regards to potential is different. Our initial potential is 0. Our final potential was E times S. So the negative charges actually move towards higher potential. That's because our initial potential was low and our final potential was high. Let's see, we said we were trying to figure out a relationship between electric field and electric potential. So I think something we've just shown here is that our electric field lines, they go out of the positive and into the negative. That's something we've studied already. So they go from positive to negative. And now we have one additional bit that we can layer in here, is they also point from high potential to low potential. So there's a relationship between the direction of our electric field and our electric potential. I think one thing we might probably layer in right here, because I don't think we've pointed it out just yet. Electric force and electric field, those are both vectors. Electric potential energy and electric potential, they're both scalars. Okay, so this is going to be pretty important. When you're doing electric potential or electric potential energy, they do not have direction, but forces and fields do have direction. Potential energy is a scalar because energy is always a scalar. And potential is a scalar because it's the energy divided by the charge. So a scalar divided by a number gives us a scalar. Okay, so that's good that we've pointed that out. And let's move on to our next little bit, where you might have experienced potential in your lives or where you might have thought about it already. So now we'll talk a little bit about some places where you might have experienced potential in your real life. The first would be lightning. So what happens in lightning is that in the clouds there are some charged ice particles. The ice particles rub against the air and they get charges by colliding together. So that leads a charge separation between the clouds and the Earth. The cloud has a big negative charge because it gains a bunch of electrons, which makes a slightly positive charge on the Earth's surface. So that creates a big electric field. And what happens is we get lightning when the potential difference between the cloud and the ground get really big. We call that a dielectric breakdown, and it happens at about 100 million volts, I think. I'd have to double check my number. So that's when we get lightning. The air just breaks down and becomes a conductor. Normally air is a very good insulator and electricity doesn't flow through it. Thank goodness, our life would be very different if that weren't the case. But when that potential difference gets really, really big, air does actually become a conductor and then the lightning flows from the top to the bottom. So that's kind of cool. Everybody uses batteries. Inside of a battery is a little chemical, little acid inside the battery. Inside the battery acid, there's a whole bunch of chemical reactions. So those chemical reactions cause the charges to separate, and those separated charges would have an electric field and electric potential between them. One of the examples we'll do, either the next or the one after that, we'll actually find the electric field of a battery, knowing the electric potential of it. And then last, turns out the cells in your body are a little bit like batteries. So there are lots and lots of chemical reactions inside your body. And between the outside and the inside of the cell wall, you actually get a potential difference. And this potential difference between the outer and inner cell is called a cell potential. If you're interested in biology or going on to the medical field, you'll probably learn a fair bit about that. So you do actually get a potential difference. It's not huge, but it's not nothing either. It's about 70 millivolts, where the outside is at the higher potential, the inside is at the lower potential. And because there's a potential difference, there's actually an electric field over the cell wall, and it causes, positive and negative ions to flow either in or out of the cell. So it leads to kind of a balance inside your cell, which makes you healthy or not. So that's kind of interesting. Okay, in the next part, we'll go on and we'll start to do some examples. Just for a little bit of fun, if you're ready for a tiny break, you might want to do a Google search for John Travolta on FET. It's just a little bit of foolishness. We get to see John Travolta scuff his feet on a carpet, and when he gets charged up enough, it makes a spark to a nearby doorknob. You might get a little bit of learning at it, or you might get a giggle out of it. Both are probably worthwhile.